Hi everyone. This is a tutorial on how you can connect to the server for this course and also how to use a GDB debugger so that it helps in your assignment too. So let's start. First of all, I'll show you how you can connect to the server that's given to you. First, you need to install Cisco Secure Client. This is for establishing VPN connection to the server. So you can download it from the web, log into it using your credentials. Uh, yes. So after this is done, yeah, it is connected. After this is done, I can just SSH into this server using my username, KUPOKH. It should be different for yours. And after you click enter, you should be prompted for password. I have set up public private key authentication, so it does not ask me for password. So after you enter the password, you should be inside your server. Let's see. So you should only be able to see this folder and this folder, this file and this folder for you. All of these have been done by me later on. So I'll show you how the executable that I emailed you. If you haven't gotten the email yet, please email me one and I'll reply to you with your executable. So I'll show you how to copy your executable that is inside your local machine to this server. So I'll remove this for now. And as you can see, this is deleted. So I'll go to my local machine. Inside this folder, I have that file I want to copy, SCP. This should do the job, but this is not working for me right now. Let's see. Yeah, it's not working. So another way is you can establish a SFTP connection. This is similar to SSH, another protocol different from SSH. This is file transfer protocol. So after doing this, I am inside the SFTP terminal, and I just need to push my profile crucial executable. Let's see. Push. Isn't this push? Let's see. SFTP push command. Put. So yeah, it is put. Oh, it's uploaded and I'll be able to see Pokral cursor. Yes. So you will have something similar in your executable. And if you go inside this, so this is a Vim command. Vim just opens a text editor for you. Let's see. Oh, all you can see is some random symbols. This is because this is an executable file. It's not readable, and it is actually 0101 sequence of zeros and ones. So this is the only thing that is given to you, and you need to figure out two pins that are unique to you. So quite challenging. So you need to do some reverse engineering, get from lower level to higher level, and try to figure out what your pin could be. For that purpose, I am going to show you a kind of simpler program and how to use that machine code to make sense out of it, to make sense of what it could be in the higher level language, what program it could be. So what I'll do is I have written this hello.c program, which is very simple program written in C. What this does is it's just as you might know, for C, the entry point is main, and what this does is it just prints some string. Then it defines some integer. This you can just define it as a int, and yes, it defines three integers in hexadecimal format so that it will be easier to see it in the memory. So three variables, and it will calculate one variable based on these three variables, and it will just print that variable into the terminal. Okay, so this is the program. To compile that, this hello is the compiled version. This was already pre-compiled, but I'll remove this hello and compile it again with GCC. you can compile this program. Oh, hello executable. Okay, so there is hello executable. This is similar to what's given to you, right? So after you're in the solver, this should be it for for the solver part. We'll now look into the GDB part. Let's try to get GDB going with this executable. GDB should be installed prior, and you can just go into the GDB terminal with this. Now you are inside the GDB terminal. Um, you can't do much right now. So what you can do is, uh, let's see, info registers. The program is not running, so we can't see the register information, neither can we see the memory information. So first thing you need to do, if you only have the executable, is since executable file, the binary file is binary instructions is one to one mappable to assembly instruction. It also has its inverse. So if it is one-to-one function, then there exists an inverse. So you can go from assembly to object code, as well as you can go from object code to assembly. So let's try to deassemble our function main from that sequence of 0101 to something that we can make sense of. So we have gotten the uh, assembly version of that main function. Uh, Yeah. So we have not touched this file at all. So we were only using the object file to get this, right? So let's try to see what this code is, one line at a time. And after that, I'll show you how to inspect the register and memory contents to um, see uh, how those memory locations and register content changes. So as you can see, uh, this is not deployed yet. So this is the program is not running. So it will show you some random memory location, and after the program is actually running, it will show you the correct location. As we have discussed in the class that this x86 architecture or SICXE, they are quite uh, relocatable. That means you don't need to have some fixed memory in specified during the compile time. It will just see where the memory is available, and it will run that program over there. So let's try to go one by one through the instructions over here. First instruction is push RBP. This is a base register. So for the register information, here is X x86. So this is x86 64-bit registers. This is the same that we are using. So these are the registers that we have over in this machine architecture, and these are different accumulator and counter. Uh, this is destination, this is base, this is stack, this is, I think, another destination register. So you can read about these all of these registers information in this cheat sheet. Yeah, so this base register is different for different functions. So this is still the previous function base register, and we need to save it somewhere. We have saved it in the stack, and after that we can use it for our own purpose. So the stack pointer points to some memory location, and that has been moved to base register. What that means is the stack pointer is now base pointer, and we will allocate some amount of memory, particularly 16 bytes of memory, to this stack. So one pointer is here, and another pointer is 16 bytes above this pointer. So there is actually a base register and stack pointer. So inside this stack, we can save any local variable of this function. After that, you might be able to see some new instructions like LEA, which is not available in SIC. So what this does is this just calculates the effective address, target address from this instruction and puts it in the accumulator, so RAX register. This is program counter, instruction pointer, it's called in x86 architecture. It adds EAC to program counter and stores that in RAX. Then that content of RAX is moved to RDI. So RDI is a special register. RDI and RSI are special register because whenever you call a function, you need to pass some parameters, and parameters are passed through these registers. So whatever is in RDI is passed as as a argument to this function. So here is a function called printf. If we see the high level equivalent, then we can see that printf is being called with a parameter that's a string literal, right? So this address of this string is passed to this function as a parameter over here. So we'll inspect how what RDI contains in later, and we can see that it corresponds to that string. Af- this is just resetting the EAX register. After that, we can see that there is three move L instructions. What this is doing is equivalent of this. It is not exactly equivalent, but what it is doing is it is transferring the some constant into some memory location relative to RBP, base pointer. So base pointer minus 10 will contain this value. Base pointer minus C will contain this value, and base pointer minus 8 will contain this value. We'll inspect the memory location later on as well. So after that, memory location is again inquired like this, and is put into EDX. Similarly, EAX. What this is doing is this is preparing for some kind of uh, arithmetic operation. So here we are adding EAX and EDX and storing the value in EDX, right? So this is equivalent of A plus B in high level. And after that, C is being loaded. Yeah, C is being loaded and multiplied to the previous result. So EDX contained the previous result, and now EAX will contain the result that we have, that is equivalent to this you, you, yeah, this operation, this result. And after that, the EAX is moved to minus 0.4 from base pointer. That means that there is another local variable that we have defined, addmol, that stays at this location. So the final result is being transferred to this address, let's say. And again, this address is being loaded into accumulator, and accumulator is loading it into SI. SI, SI, as I said, DI and SI registers contain the uh, parameters to be passed for function call. So since printf is being called over here, uh, printf has two parameters, the type of data that it wants to print and the actual data. So actual data is the second parameter, right? So it is stored in SI, and this this location gives the information about percentage D, which means that it is the integer that we want to print. So this is being loaded to RAX and finally to RDI. This is the first parameter. This is the second parameter. So the call to function printf happens over here with these two parameters. Hopefully you got some idea. Now let's run the program. To run the program, what you can do is you can just run. First, let's just run. After running, we see the welcome to addition program, which we printed, and also see the result that we wanted to print, right? So this was just running the whole program at once. But let's try to insert some breakpoints so that we can inspect memory locations, memory locations and register contents. Okay, so break main, and let's just run it, or let's continue, not being run. So yeah, so for the sake of clarity, I'll just add this as well. So yeah, it will show me where the program counter is right now. As you can see, we're already at solve this instruction. This is a boilerplate code, so it happens for all the functions. So we're already at this point. Now, if I want to go to next instruction, then I can do ni. And by the way, all of this is available over this page. Okay, so you can find all of the available commands on GDB over here. Mm, yeah, so this happened, right? This hasn't happened yet. So this is the next instruction that will happen. So let's look at info registers right now, and let's see what arrayx has. Arrayx has some kind of value. After this instruction, this is not yet run. So let's run this instruction and see the content of arrayx. Info registers. Yeah, it has changed, right? So from 149 to 6008. So this is how you can inspect the content of registers and what's happening, and try to make sense of what's happening over here. So let's break at some interesting point, okay? Let's break at this instruction. So I'll just deassemble again, because this is not the true address that we need. This is not the true address because the program was not being run. So this was just a placeholder. Right now, it will show, since the program is being run, it will show you the true address. So I'll just deassemble again. Yeah. So we got the true address. Let's break at this. To break at the address, you need to provide some asterisk before the address. And okay, I'll continue till then. So yeah, so this is executed. Now, as I said, RDI contains the parameter value. Parameter is welcome to addition program. So since this is a string literal, it will contain the address of this first character. So let's see. Let's inspect registers RDI, right? So yeah, this RDI, you can either do RDI or yeah, you need to do the RDI. You need to look at RDI. Let's look at RDI. So you can inspect the memory contents like this. Put X first and then just keep the memory location. Okay, I got something like this. This is the first byte. This is the second byte, and it is increasing. So this first byte is at 08. This second byte will be at 09. So if I just go and do 09, then I'll get 65. As I said, this is the ninth 09. This is 0A and so on. Okay. Yeah, let's just see what 57 means. Okay. Converting from hexadecimal to ASCII, we get W. So this is the start of this uh, string literal W. So if I go over here and look at 09 content, then I'll get E. And if I do this again, I'll get L. So yeah, you get the point, right? Um, so this RDI was sent as a first parameter to this call function, this printf function. Hopefully you get that. And after this, let's try to break at somewhere around, okay, this one. Make break. Oh, Q. What happened? Oh yeah, I need to provide asterisk. Okay, now continue. Yeah, we have continued till this instruction, and let's also execute this instruction. So yeah, all of the assignment is done now. If I want to see if it actually stored 06 600, this is in hexadecimal, into this memory location, then what I can do is I can just info registers. I need to look up RBP, this one, RBP, and then subtract. I can subtract any value, like let's subtract 10 and see if this value is stored over there. 10, calculate. Okay, copy this. See the content of this. Yeah, 1123. You get it right, because 1123 was stored in relative to RBP. RBP minus 10 in hexadecimal contained 1123. And one big thing you need to notice over here is, what is this format called? When you store multi-byte register into memory, you can either put the highest byte in the lowest memory location, or you can put highest byte in the highest memory location. What this is doing is, this is putting the lowest byte in the lowest memory location. So D0 will contain 2, 3. This is the lowest byte, right? And if I look at D1, then it will contain 1, 1. So this means higher byte is taking the higher position and lower byte is taking the lower position. And this is called Little Indian format. So I actually got confused between Little Indian and Big Indian, but I probably think this is Little Indian. Please look it up. And yeah, so we can also inspect if this value is being stored in this value, this memory location, and so on. But I won't show that, and I'll just move on to let's see, result. It's storing result in this memory location. Okay, so each integer will occupy 4 bytes. So 10 is 16, then C is 12, then 8, then 4. So we have 4 local variables, and uh, it has allocated 16 bytes of memory stack for this function. So based on the local variable, it has allocated the space, and we have almost consumed all the space, this 3 space, and this is left. So let's just go over here. I'll add break at this point. Okay, and continue. Yeah, so it should already have the result in this value. So RBP is same. Instead of 10, I'll do 4, calculate. I'll get the memory location. I'll inspect the memory location. So seems like this is our answer, 86D000. And if I go and calculate, let's say, what is 1123 1123 plus 555 555 1678 multiplied by 600, 86D00. So yes, this was the result that got stored in this memory location, on this memory location, that was pointed by the base pointer -4. So we have almost consumed all the stack that was available to us, and also all the local variables are already done, so we don't need any more space. Finally, let's look at this printf and these two parameters that's being passed. Um, I'll go here and see what ESI and RDI have stored. Okay, I'll just go here, break at break at. Okay, I'll just continue till then, and I will inspect those two registers, RSI. RSI, yes. So this is our result that will get printed. And RDI, this is the location of this string that will get passed on to uh, the printf. So this is probably it. So if I continue this, the everything is already done, and this will print those values that this these two printfs wanted to print. Uh, yeah, this is it. So based on this, I think you might be able to solve the assignment question, but you need to read more about some registers, some functions like some instructions like LEA, uh, move L, and so on. But I think this basic knowledge of GDB and connecting to the server should equip you with at least getting started on the homework, and you'll at least reach somewhere. But I've tried being uh, as detailed, I think, as possible in this video. But if you have any questions, please feel free to reach out. You know my office hours, and I'll also stay after the class. Hopefully, you can do the assignment now. Thank you.